Okay, so hello everyone. Today we are much honored to invite Professor Konstantin from PSI to give us a lecture on the Phenix and Superphenix Sodium Fast Reactor static and transient benchmarks. So, Professor, let's welcome him to give our detailed introduce on this topic. So, please, Professor Konstantin.
Thank you very much, Professor Chen. Good afternoon, everyone. We start. Yes, I would like to start with the goal of the lecture, and this is simple. I would like to present you a few open data sets which you can use for validation of computer codes intended for neutronics, thermohydraulic, and core mechanic analysis of sodium fast reactor with MOX fuel. So the outline of my lecture, it will consist of two parts, approximately equal, I hope. The first one will be about Phenix sodium fast reactor, and second about Superphenix. And I start in both with short introduction to tell you a few words about these devices, these reactors. And then for Phenix, I would like to present you several end-of-life tests, in particular control rod shift test, which is a static neutronics benchmark, the natural convection test, which is coupled transient neutronics and thermohydraulics, and finally core flowering, which gives us the possibility to validate static and transient coupled neutronics and mechanics. So this is first part for Phenix, and second part for Superphenix is based on startup tests, and also they consist of two parts. The first is static neutronics benchmark, and second is transient neutronics and thermohydraulics. So all these data are openly available, and I will also give you references where you can find additional information. You can also leave comment on this website or send me email if you need additional explanations. Okay, I start with Phenix. So this is a plant view. Phenix is a French reactor built at Marcoule site, close to Marcoule city and Orange city in the south of France. So here you see a lot of details, the core and the secondary system. This reactor operated from 1973 until 2009, and in 2009 it was shut down, and before starting decommissioning they decided to conduct so-called end-of-life tests. So this what I'm going to present you today, these tests. Yeah, this is a classical pool type sodium cooled fast reactor with all elements shown here. There is small core surrounded by thick neutron protection and shielding, in particular to protect secondary sodium in intermediate heat exchanger. So it's located here. Then there is a fuel transfer arm shown here to reload and load the assemblies. There is a rotating plug, primary pump you can see on the right, and control rod mechanisms. And Phenix also had quite special organization of internal vessels. Yeah, there was a let's say classical double vessel, but also there was a primary containment here surrounding the reactor vessel. And also inside the pool, there was a conical support collar. So this is important that Stromberg and Diagrid were supported by this collar. So they did not stand on the bottom of the vessel, but they were hanging. And this had impact on the thermal expansion mechanisms, which are very important for reactivity feedbacks, and we will talk about this later. So these are general characteristics, like thermal power was designed to be 563 thermal megawatt, electrical output was 250. Although we will touch today some negative, so-called negative reactivity events occurred 4 times during Phenix lifetime, and there was a lot of research and efforts in order to give the explanation of these events. But finally, the decision was to significantly reduce the power to avoid repetition of these events. And also, I can say that very clear explanation or unique explanation was not found. There was a lot of hypotheses of this event, and we will talk about some later today. Okay, you can find here other parameters like inlet, outlet, primary and secondary sodium temperatures, and primary sodium flow rate is 2.8 ton per second, and also parameters of water, tertiary fuel, coolant. There was very special design of steam generator, so I made a slide to show you. So there was a housing, a box, yeah, which has this shape, and inside this box there was a lot of tubes shown here. So it's a tube where sodium was flowing from up downward. So here at the top is sodium inlet, and here sodium outlet. And also there was different sections of steam generator, like economizer, so water entering from below and go up, so it's counterflowing heat exchanger. And then there was economizer at the bottom, evaporator, superheater, and reheater. And the feature of this steam generator is the water pipes were located inside sodium tubes, as shown here on the right. And there was, as I said, also insulated housing. And what is not shown here, there was an inlet and outlet windows, the doors, which can be closed, which can be opened. Normally they are closed, but they could be opened. In this housing, in this box, there were windows, and if you open them, then the atmospheric air could circulate through this housing and remove heat from the surface of steam generator. As you can see, there is a lot of surface, and in this way, this is a mechanism of removing decay heat. again, we will talk about this later. This is the diagram of the whole system. You see reactor building, you see the pool, primary pool with 3 primary sodium pumps, 6 control rods and 1 shutdown rod, and 6 intermediate heat exchangers. So every 2 eye checks, intermediate heat exchangers were connected to 1 secondary loop. So in total, there was 3 secondary loops. So you see a sodium pump secondary, and the steam generator we just discussed, and then electricity generation system, which includes turbine and so on. So I already mentioned that in 2009, before starting decommissioning, the CEA and EDF, they decided to conduct a series of end-of-life tests. So I listed here some of them, and the list is not complete, but I think it's quite a significant database, which almost all tests are available for using for validation of computer code. So the first one is the symmetric test. I did not participate in this test, so I don't present it today. But there is a link here, and you can find very detailed description. So this test was a part of CISAME European project, and it was devoted to thermal hydraulic analysis of pool behavior of primary sodium in the pool under conditions when perturbation come from one loop, only from one loop. And this creates some asymmetry in temperature distribution and correspondingly impact on natural convection. So what I'm going to briefly present you now is 3 end-of-life tests. The first one is control rod shift, the second is natural convection, and the third is co-flowering. So we start with control rod shift test. As it follows from the name of this test, this relates to the core, and this is basically neutronics exercise. Although, in fact, the power distribution were defined using thermocouples, using, as you probably know, every outlet of every assembly was instrumented with 2 thermocouples. So we were able to measure the outlet coolant temperature distribution at all assemblies with fissile fuel. And this gives us possibility to use this measurement for measuring power distribution, for steady state conditions in this test. So the idea here, you can see on the left the map of the Phenix core with 6 control rods and 1 safety rod in the center, but safety rod was not inserted in this exercise, but all 6 control rods were manipulated. So you see one of these 6 is red, marked as red, and 1 marked as blue. And then on the left, you can see 4 configurations used in this exercise. So the majority, the first step was with the same level of insertion of control rods. So it was most uniform power distribution. In the second step, all control rods were slightly withdrawn and 1 blue one was injected. So it's created some deformation of the core power distribution. And I must say, important that reactor power was kept the same for all configurations. So they exactly compensated the perturbation. They injected blue control rod, but then they withdraw all others in order to reach again the same power. Yeah. And then they measured the steady state outlet coolant temperature distribution, and this gives us possibility to interpret and to find power of every assembly. This was the second step. The third step was injection of blue and withdrawal of red control rods, and then compensation with other four. And the last step four, was just injection of withdrawal of red control rod, and then compensation with the rest 5. So 4 configuration. And the idea here that using these temperature measurements, we were able to recalculate assembly-wise power distribution. And then we can calculate, we can record the deviation of every step compared to step 1, which was most uniform power distribution. Then we numbered assemblies, so I go back here and you can see the numbering scheme. The number 1 is the first, and then we go by circles from 2 to 7 as the first ring. Yeah, from 8 to 19 is the second ring, and so on. So now we plot here the deviation of step 2 from step 1. As you remember, this step is insertion of blue control rod, and then the power was suppressed around blue control rod and increased around red control rod, just symmetrically. Yes, when you push the power map somewhere, the neutron flux, in one point that you observe the increase of the neutron flux at the opposite symmetric position area. Yeah, we can see this on this curve. Yeah, well, so we go, as you remember, by circles. So this is the first circle, then second ring, third ring, and so on. And we always see that when we arrive in our ring toward blue control rod, we see the suppression of power like -5, -10%. And on opposite, when we close to red, then we have increased of power around 5%. So it's quite non-uniform deformation of power. And you see here that we managed to reproduce it with our tools. We use at PSI. These are Trace Sparks, which is diffusion solver, coupled to Trace system code. And also we used CEA Eranos static tool in this exercise, and we compared with measurements shown also here and received quite reasonable agreement. Then we have comparison of step 3 against deviation of step 3 from step 1, and here we have more linear perturbation when we go ring by ring, because now we have symmetric withdrawal of red and insertion of blue control rods, and we have relatively symmetric perturbation, like plus 10% around red control rod and minus 10% around blue. Again, very reasonable agreement. And finally, step 4 is withdrawal of red control rod. So we see the increase now, sharp increase of power around this position, and then some suppression, smooth suppression in the opposite position. So that's all for control rod shift. This is very good exercise for validation of coupled neutronics and thermohydraulics. You can find detailed specification and test data and results of other code prediction at this open publication. There was a IAEA coordinated research project, and there is a nice TechDoc document. So we can continue with natural convection test. So now this is mainly thermohydraulic test. We should look at the Phenix primary and secondary system, and I show you the 3 phases of this exercise. So the phase 1 started at time 0, was feed water shut down. So it's here, yeah. You see the feed water, cold feed water injection, and it stopped for 1 steam generator. So I should say that in this exercise, the power was reduced. 1 secondary loop out of 3 was disconnected. So 1 loop worked as usual, and 1 secondary system was perturbed. And in this 1 out of 2 operating, the feed water was shut down. So this phase, nothing else changed. So the primary and secondary pumps operated, and we just had the reduction of heat removal. So it was unprotected loss of heat sink. So the scram was also not activated. So this phase was for 8 minutes. So we have 8 minutes of unprotected transient at real reactor, and we can use it for validation of reactor kinetics coupled to thermohydraulics. Then after 8 minutes, the scram was operated and primary pump was tripped. So the idea was to have reactor under conditions of transition from forced to natural convection. So for this reason, all primary pump was switched off. The secondary pump did not trip, but their rotational speed were strongly reduced. Okay, so for primary sodium, we rely on natural convection, and for secondary system, it was forced and natural convection together. So this phase of transition from forced to natural convection lasted 3 hours. And after these 3 hours, the next step was opening of steam generator casing. So I already showed you steam generator, and I told you that there were windows or doors. And these windows, after these 3 hours and 8 minutes, were open. And this allows atmospheric air enter the casing and remove decay heat. Yeah. And now this last phase lasted 4 hours. So we, in fact, we found this possibility to analyze unprotected part of phase 1 at PSI, and we did it with our tools. We used Serpent and TraceSparks. So the transient start at 21% power only and 46% flow rate, and at 400 degrees inlet temperature. And the perturbation, as I said, was a dry out of 2 out of 4 steam generators. So this led to increase of inlet core temperature, right? So we stopped feed water, the heat sink was deteriorated, and inlet core temperature or outlet ICHEX temperature of primary sodium starts growing. So this was recorded. This data is available. So we have core inlet temperature history as a function of time. And scram, as I said, was after 8 minutes. So we created a trace model, very simple, with 4 channels in inner core, outer core, with different plutonium content, then a blanket, and then the rest, reflector and bypasses. And we have inlet plenum and outlet plenum, and we connected some heat structures to this simple system, in particular digrid. And also we simulated fuel, and according to benchmark, they give us specifications that 90% of fuel assemblies was with closed fuel-clad gas gap, because it was end-of-life experiment. So the fuel was burned, yes, with high burnup, and they estimated the probability or amount of fuel rods in which the gas gap is closed and the fuel is in solid, hard contact with cladding, and it was 90%. So we simulated so separately with 2 heat structures, linked fuel and free fuel for inner core and for outer core. And for blanket, we assumed free fuel. Okay, so as boundary conditions, we used core inlet temperature and flow rate and outlet pressure, as usual. So we relied both on point kinetics with trace and special kinetics with trace sparks. So for trace, we used simple feedback reactivity model, and we take into account the Doppler reactivity feedback, fuel expansion, digrid radial expansion, and vessel expansion. So this is the results for unprotected loss of heat sink. So this I took these results from PhD thesis of Aurelia Sheno. You can also find openly in internet for more details. So you see here the reactivity as a function of time and power as a function of time. So for reactivity, this is results of point kinetics calculation with decomposition according to the reactivity feedback I just mentioned, Doppler digrid, fuel, and vessel expansions. And the experiment, you see here total reactivity measured in the experiment. So it starts from 0 and then becomes negative, go down and then go up again and stabilizes around -10 ppm. So we are able to reasonably reproduce the shape with some deviation as the minimum value. And below you see the measurements of power and the predictions of trace, black curve, and trace Parkes 3-dimensional red curve. So for Parkes, we use serpent model, and we benefit here from the control rod shift experiment, because there in this test we created the serpent model of the core, and then we can use it to generate multi-group cross sections for different state variables, what we need for Parkes. So we obtained reasonable agreement between 3-dimensional and 0D predictions. So when you look to reactivity decomposition, we see the positive Doppler, which means that the power goes down and fuel temperature goes down, and it is compensated by negative digrid expansion mainly. Okay, so the coolant temperature goes down and digrid temperature also goes down, and then the radial dimensions is slightly reducing, and this reduces also the pitch between assemblies. So when assemblies becomes closer, then the sodium amount in the interassembly gap reduces, and this has a negative effect to the reactivity as opposite to void effect. Yeah, when we when we decrease the amount of sorry, it's not increasing, it's not decreasing, it's increasing. Yeah, the pitch is increasing and amount of sodium between assemblies is increasing. So we increase moderate, we increase slowing down power, and this shifts the spectrum towards thermal spectrum less fast, yeah, and it has negative effect. It's also interesting to see that the fuel expansion effect from fissile region and fertile region have different signs. So it's positive for fissile and negative for fertile. And the reason here is that the blanket fuel is heated, in fact, by the temperature of the blanket fuel is increasing because inlet sodium temperature is increasing, and this hot sodium is heating the blanket fuel, and this is a negative Doppler, while in fissile region it follows, it's the same trend as Doppler, so its temperature is going down because of reduction of power, and for this reason the fuel expansion is positive. So we conducted a number of sensitivity studies to understand the importance of core inlet temperature, fuel clad gas gap conductance, and fuel expansion mechanisms. So this gives us in particular understanding of importance of these different mechanisms of fuel expansion for fissile and fertile regions. Then we also calculated the whole test. So this was really the goal of the test, to validate our thermohydraulic codes, how good these codes for predicting transition from forced to natural convection. And here you can see the results. So for this calculation, it was the whole 7+ hours, and we used power as a boundary condition. Yeah, it was provided in the benchmark. You can see in the red, this is power. You see the first phase before scram where power is reducing, as shown on the previous slide, but now it's not calculated, it's experimental measurements. Then scram results in shutdown of reactor and its decay heat level, and then pumps trip occurs shortly after scram, and then we have some flow rate calculated by trace. In this case, everything is in logarithmic form scale, both x and y axis, and after 10,000 seconds we have activation of third phase, started with opening of 2 steam generator containments and cooling down the steam generator surface with atmospheric air circulation. So here you can see 2 identical plots. The top is calculated results and the bottom is measured experimental results for primary coolant temperature. So we have several points here: core outlet in red, IHX outlet in violet, and then pump inlet in green. Yeah, we can compare these three between calculations and experiments. In calculations, we have also core inlet, just for information, in blue. So we can see here that during the first phase, the core outlet temperature is almost constant with slight reduction, yes, and IHX outlet and pump inlet, so it's both cold pool temperature, yes, is increasing because it's unprotected loss of heat sink. Then for the second phase, we have transition from forced convection to natural convection. And here we have significant discrepancy. And this is understandable because transition is very much three-dimensional effect. And here we used a simplified trace model with one-dimensional or two-dimensional simplified modeling. So this is the area where we can apply improved model like computational fluid dynamic or DNS in order to better catch the flow pattern during this complicated transition. And for the third phase, when we have the heat sink in the form of circulation of atmospheric air, we have more stable cooling of the primary system. And here again, with establishment of established natural convection, trace is doing a good job again. So we have a very reasonable prediction of the rate of the cooling. That's it for the second test, which is a natural circulation test. Again, we had IAA CRP, so French side CEA shared the results, and it was a very fruitful exercise with many partners, and it resulted again in TechDoc. You can find in open access to have detailed specification, test data, and results of code predictions. The third test I would like you to show in the first phase is so-called core flowering test. So this was a mechanical, mainly mechanical exercise on deformation of the assemblies, deformation of the pitch between assemblies. As I mentioned, the negative reactivity event occurred 4 times during the lifetime of Phenix, required explanation. And the goal of this test was to see if the reactivity effects from deformation, from co-flowering, increase of the pitch at the top of the reactor, if this effect can be the reason of reactivity perturbation observed in negative reactivity anomaly events. So in other words, the purpose was to investigate core compaction in a sodium fast reactor and assess neutronic consequences of mechanical core deformation. So it was coupled mechanics and neutronics. So how they achieve this deformation? They designed in-pile device shown here, and they inserted this instead of the central safety rod. So this device allowed to push from above, apply the force from above to piston, and then resulted in a radial deformation. So this device pushed the first ring aside, as shown here on the right, and then the first ring deformed the second ring, and so on. So they could create different configurations, different deformations, and then they measured assembly displacement, flowering forces, and reactivity signals under different temperature conditions. So I will show you how we use this data in another PhD study done by Janusz Body at PSI, and how it can be used not only for static, but also for transient analysis. So first of all, we made a plan. We aimed at development of methodology of coupled neutronics and mechanics, then calibration of this methodology using Phenix End-of-Life co-flowering test data. The third is we would like to model transient core geometry perturbation. So it's not anymore the core flowering test because it was static. But we decided, okay, let's try to make deformation like this and then let it go. Then we see how transient goes, how the assemblies deforms, how they compact and then jump back, yes? So we decided to create a tool and make this analysis, and then we decided to qualitatively compare with measurements in this negative reactivity event. So AURN, AURN is an abbreviation in French, which means negative reactivity anomaly event. This is our modeling methodology. So we used two codes, Autodesk Inventor Nastran for mechanics, you see on the right, and then Serpent Continuous Energy Monte Carlo Neutron Transport code. So we started with the force. It can be static force, but in general, it's time-dependent force or load. Yeah, when we apply the load, we on the model created for Nastran, then we can make dynamic mechanical finite element calculations and produce co-geometry snapshots. So for every time step, yeah, we produce co-geometry. And then we can make like 100 or 1,000 or whatever number of snapshots. And for every snapshot, we make Serpent calculation. So we created the methodology where we can use output Nastran file as input for Serpent. So we did not develop every time text format, but we used cut drawings, yeah, cut results, and we feed these files into Serpent, read the geometry, detailed geometry, and made calculations. In Serpent, we didn't use heterogeneous geometry. It would be too difficult, but we homogenized every assembly. And this calculation allowed us for every snapshot to calculate reactivity, and then as a function of time. So, and then we take this reactivity and with simple point reactor kinetics calculations, we converted this reactivity to power as a function of time. So this is a methodology we used. We start with just a check, with sanity check, verification. We created undeformed geometry, uniformly deformed geometry, shown here, just uniformly increase the pitch, and then non-uniformly deformed geometry, like flowering. So, and then we calculated with Serpent the K-effective of different configuration of reactor lattice, and we compared in particular text-based input with Nastran geometry-based input, what I just explained. So, for example, uniformly deformed geometry we can specify with traditional Serpent input, but we also can generate the input from Nastran with this coupling. And we obtained very good agreement as shown here in the first two lines. So it was verification. And next, our plan was to calibrate and validate our methodology on static measurements of co-flowering test. So we had measurements, first of all, of assembly top deformation as a function of vertical piston displacement. So the displacement in vertical dimension, like shown here, from 0 to 90 millimeters, is converted to first ring deformation, and then these measurements are for fifth ring, for disassembly. So we applied our model and calculated the disassembly deformation and compared with measurements, and we obtained this good agreement. So here we calibrated Young modulus, the elasticity modulus of our homogenized assemblies in order to reproduce these results, the measurements, as good as possible. And then for every core configuration, we put the model into Serpent and calculated reactivity. And we have measurements of reactivity for every test, for every deformation. Yes, and as you see, we obtained very good agreement. So the effect is negative, and again, we already discussed it. And when the pitch is increasing between assemblies, we have, for the same amount of fuel, more sodium. This has a negative effect because of the spectral shift. So fast reactor becomes less fast, and this has negative effect. And this is quite significant. So with maximum vertical piston displacement of 80 millimeters, we have minus 70 ppm. So it's quite significant reactivity effect. So as intermediate conclusion, we can say here that we calibrated Young modulus of homogenized subassemblies to reproduce deformation measurements with Nastran, and Serpent calculation done for geometry snapshot are in good agreement with reactivity measurements. So as I said, now we decided, okay, we have a tool which is transient, and let's apply this methodology for perturbation. So we make a shape of the load of force, which we applied on this first ring. Yeah, and it has this shape from 0 to 10 milliseconds. It goes from 0 to 100%, then stay constant for 10 milliseconds, and then go down with the same rate in 10 milliseconds to 0. So I must mention here that one of the hypotheses, was of these events was mechanical deformation of the core, and one of the reasons of mechanical deformation was boiling of sodium. And when we have sodium boiling, then the bubble can collapse and create pressure spike. And we also did this analysis in this PhD, and we showed that we predict power, we predict pressure shape, which is similar to this shape, which we used here. So when we applied this load, this pulse of the force, then we observed the dynamic deformation of the core. And here we show 10 rows. Yeah, we take 10 assemblies in a row next to each other and make the plot. So we first have strong deformation of the first row, then the second with some delay, and then with some delay they go like to the side, and then they go back, and they go even compacting. You know, you see they cross the zero, and then they become even closer than in nominal conditions because of the mechanical inertia when they go back, and then there are some oscillations. So these are natural oscillations of the Phenix geometry. And then we take several snapshots for these geometries, and with Serpent we predicted reactivity, and you can see it in black. So when we apply the force, then reactivity becomes negative, then it goes back, oscillates, and then becomes positive. It goes roughly from -10 ppm to 5 ppm, and then it continues oscillation, but then we stopped at 0.2 seconds. So as I said, the last step was conversion of reactivity to power, and here you see the results. Power goes down, and then up and down again. And here we take the measurements of our events. As I said, these events resulted in reactor scram, so it was oscillations of neutronic signal. Here it's made equivalent to megawatt to power, and there was automatic shutdown. For the last two events, we have measurements. So we decided, okay, we don't know what happened, but let's just overimpose, let's just put these signals on our results. And this is what we saw. So the blue is measured results, and the green is our predictions, just arbitrary deformation. So we were, in fact, quite happy because we see the trend at the beginning, and we even reproduce some frequency. So one of the possible reasons is mechanical core deformation, and we qualitatively confirm that the level of reactivity perturbation which we obtain from our model, from our perturbation, is consistent with what was observed in these events. Then we decided to make a small sensitivity study, because in Phenix End-of-Life Tests, the distance between the top pads was set to 250 micron, and it was hot zero power conditions. So you can imagine that the assemblies are parallel to each other because they are all at the same temperature. But in reality, in Phenix, when these events occurred, the reactor was at hot zero, at hot full power. So there was different temperature at the bottom and at the top. And this resulted most likely for closure of the gap between the pads, because expansion at the top was higher than at the bottom. So we repeated our calculation, but now with zero distance between top pads. So all assemblies were in contact. And this is the result. So we see similar deformation, but qualitatively, but quantitatively, the pattern was quite different. And now we compare the resulting power with our measurements, and we obtain even better agreement. So this is all I would like to tell you about Phenix, these 3 tests, 3 benchmarks. So you can look at Janusz Body thesis available online for more data and results on modeling Phenix End-of-Life co-flowering test, and also this exercise on transient deformation. Okay, I am ready to continue with Superphenix. So if you don't mind, we don't make a break and we keep the questions at the end. So Superphenix. So this is a big reactor operated in Crémalville in France, close to border with Switzerland. And it was operated from 1985 to 1997, around 12 years, you can see that it is bigger device, bigger primary system and secondary system also. Here you can see the primary diagram with the core and the control rod system, hot pool, primary pump, intermediate heat exchanger, then strong back. In this case, strong back was sitting on the bottom of the vessel, then diagrid and the core. You can see here the parameters. So the thermal power is 3000 megawatt, and the mass flow rate of primary system is 16.4. So it's much bigger reactor. And for this reactor, I would like briefly to show you two tests: static neutronic and transient reactor kinetics. So for static neutronics, we developed a benchmark in frame of European SFR Smart project. So this is a core radial map of SuperPhenix. We have inner core subassembly in yellow, outer core subassemblies in light blue with different plutonium content, and then there is a radial blanket in green. So there are diluent subassembly 18 and 21 control rods and 3 shutdown rods. So we developed the detailed specification of the core in terms of geometry and material composition. Everything is published in open access. Here you see the axial composition of the fissile, fertile, diluent, and control rod assemblies with axial dimensions, 4 sets of axial dimensions for different temperatures. Because in this way, we can calculate different reactivity effects. We can calculate the effect of thermal expansion of different parts of the core. So we formulated 13 configuration criticality cases, and we provide results for these 13 cases. So I grouped them in 3 groups. The first group is cold zero power states for different temperature. We also distinguish temperature for cross sections and temperature for geometry, because this allows us to calculate separately Doppler effect and separately expansion effects. We also have different cases with control rod insertion by 100 centimeters or by 40 centimeters. The second group is hot zero power, and the third group is hot full power. Okay, also we have some cases with the control rod insertion. So case 7 we called conf1, like reference configuration, and we present the results as a deviation from conf1, like reactivity effect from this reference configuration. You see it in the center. So there are 7 partners, 7 codes used, participated in this exercise. And you see here the effective or deviation of multiplication factor from conf1. And for these 4 points which are lower, these are cases with inserted control rods. And the most inserted here, case 4, we observe the highest discrepancy. So the main reactivity effect relates to the left y-axis, and the deviations, dash lines, relates to the right. So you see that we have reasonable agreement, except for this case 4. Everything is within, I would say, 200 ppm, the discrepancy, which is very reasonable. We also naturally compared fissile subassembly power, radial distribution. You see it in blue here. you see it in many colors. Yeah, it's every point is for separate code, and this colorful point showed us the deviation from the reference solution, and reference solution is in blue, and this obtained with Serpent. So again, we see very good agreement, except maybe one code, Dragon code, we are within 3 plus minus 3%, which is reasonably good for diffusion codes. Then we compared also Doppler constant and its components. Components in space, yeah, Doppler from inner core, outer core, radial blanket, and axial blankets and total. So you can see again the results and discrepancy, everything documented in the paper in tables. So you have numbers to compare with, and the same for void effect. Again, for different configurations, for different regions, and for inserted and withdrawn control rods. So this is all for the first part, static. Neutronic benchmark, you can find all details in this paper by Alexander Ponomarev. It's open access paper, and you can find much more data listed here. And finally, the last part of my lecture, I would like to give you very brief, very quick presentation of transient reactor kinetics benchmark. So this benchmark we developed based on the one publication in Nuclear Science and Engineering. So shortly after commissioning of Phenix Superphenix reactor, France published a detailed special issue of Nuclear Safety and Engineering journal with a lot of data from startup tests. And in particular, then they presented 6 transients. So we take this journal, we digitize the plots, and we developed on this basis, and on the basis of static benchmark, which gives us the Serpent model, reference Serpent model, we believe in that it's quite close to real reactor. So we developed 6 transient benchmarks. So these benchmarks are for system codes. So very simple. This is example of trace model with just 2 channels. In fact, it was 4 channels, but it doesn't matter. So it's a very simple model which allows us to use boundary conditions. So what is important here, that we connected heat structures to simulate vessel Stromberg diagrid and control rod drive line expansions shown here. We just connected them with inlet and outlet temperature. And of course, we have heat structures for fissile and fertile fuel rods. So the boundary conditions here were core inlet temperature and flow rate and outlet pressure. It's similar to what we did for Phenix, for first phase of natural convection benchmark. So we used point kinetics model with Doppler fuel expansion, coolant expansion, diagrid, Stromberg, vessel, and control rod drive line expansions. So as I said, 6 transients. They are shown here on the plot in terms of reactor power and inlet temperature. And they are listed on the left in 3 groups. The first group is reactivity insertion. So at hot zero power and 179 degrees isothermal conditions, the 30 ppm were injected, and then power increases. Yeah, it's called self-stabilization test, and this is 0.1 here. Yeah. Then another reactivity insertion was minus 50 ppm also with reduction of inlet temperature at 692 power and 389 temperature. This is case 2 shown here. And finally, the larger power and larger reactivity insertions, minus 74 ppm in 3 steps at 50% power. This is case 3 shown here, the maximum power. And then second group is primary mass flow rate reduction, in both cases minus 10%, but again at different power level. So it's like 20% case 4 here, and almost 50% case 5 here. And finally, there is an inlet temperature reduction, which is similar to, again, Phenix exercise, but different sign. Yeah, the inlet temperature increased there, and here we have inlet temperature reduction. And this is case 6. So you see that cases 2, 4, and 6 are grouped together, and in fact, they were one after another. So they first inserted negative reactivity, case 2, then after transient and stabilization, they decreased primary mass flow rate, case 4, and finally they changed the secondary system pump rotational speed in order to reduce inlet temperature. This is case 4. So they are connected. Now I have few slides for every case, and I try to go quickly. Case 1, positive reactivity insertion. Okay. You see the parameters we start with. So it was withdrawal of control rod. And then in some time when perturbation propagates through the primary system and enters again, we have in 1000 seconds slight increase of inlet coolant temperature. So there were 3 codes: trace, SIM SFR, trace from PSI, SIM SFR from Karlsruhe, and ASLET from Hasdare. We calculated this reactor power. It starts from 0, yeah. It goes up and then down and then stabilizes. This is very difficult transient to calculate because you need a very good fuel behavior model to predict correct evolution of fuel temperature. So here you see reactivity components. We always make 2 groups of curves. One group for the left axis with, in this case, it's the same scale, but with these 2 axes we can shift and make comparison easier. So the total reactivity in blue solid line is on the left, so it's 30 ppm insertion, and then it goes down, becomes negative, and then slowly goes up. The other reactivity feedbacks here are negligible. This is sodium expansion and fuel expansion. So we started from 0 power, so they are not important. But the bottom group is for the right axis, and here we see negative Doppler because fuel temperature goes up, but also we see negative differential control rod. And this is because we have a slight increase of outlet coolant temperature, and this results in heating up of control rod drive lines and slight injection of control rods in the core. This is very delicate effect to predict also. So the second also reactivity insertion, the second case, but negative, it's at high power, 23%, and 50 ppm negative reactivity insertion. We have inverse picture. Yeah, before we have increase and decrease. Now we have decrease and some increase with stabilization. Again, all 3 codes are very reasonably with prediction. And now The bottom group is for the left. This is total reactivity, sodium reactivity in blue, and brown is fuel expansion. And you see now the scale is very, very low. Everything is very low in this group. But for the right axis, we have top group with Doppler, which is now positive, and also positive control rod withdrawal. Yeah, differential control rod effect is withdrawal. Why? Because we injected negative reactivity, outlet coolant temperature goes down, drive line becomes slightly shorter, and injected. We could also have here vessel effect. In all cases, we observed vessel expansion effect. And this is very important. It goes with large delay, but we always see it. And also in yellow, you see here digrid radial expansion. So coolant temperature goes down, and assemblies become closer to each other. Sodium amount decreases, and this is positive effect. So with this very small perturbation, yeah, very slow, we are able to catch all significant effect, including mechanical, including thermal expansions, in different combinations, because we have similar perturbations, but at different power level. And this gives us the database to get confidence in our tool when we apply this tool for bigger perturbations. Okay, then case 3 is what I just said, negative reactivity insertion at a high power level in 3 steps of -25. So power goes down and then slightly up and stabilizes. So the same pattern. It's just different level of all reactivity feedbacks. The next group is primary flow rate reduction, and we start with this 22% power, and the flow rate is reduced by 10%. It's also accompanied by reduction of inlet coolant temperature, because when we reduce the flow rate in primary system, that heat exchanger becomes more efficient. It cool down stronger, and then for this reason the inlet coolant temperature with some delay is decreasing. So we have quite complicated shape, reduction, increase, reduction, stabilization. And we didn't catch very good the second increase, but you can believe me that it was incredibly complicated exercise to create the model which catch all the interplays between different thermal expansion and Doppler. So you can see it here. So how complicated the thermal expansion, for example, is, and this light yellow or light green curve shows oscillations. And this is differential control rod. So it includes vessel expansion, control rod drive line expansion, digrid expansion in their combination. Okay, similar exercise for high power, similar shape, yeah, more oscillations. So it's even more interesting because now we propagate the perturbation several times through the primary system, through the eye checks. And this is a result in terms of reactivity. Again, the same physics, but different levels of temperatures and power. And final case is inlet temperature reduction. And here we have simple case because the main reactivity feedback here is digrid contraction, yeah, reduction of radius. And indeed, we see here positive effect from the yellow curve from diagram radial expansion. But we observe here also strong effect from the vessel. And this complicated behavior of control rod motion. Okay, so we have this 6 transient benchmark, which allows you to test your transient system code for sodium fast reactor. And you can find all details. So we created this paper with all specifications, with all numbers in tables, all time histories, everything you can find in this paper. Okay, so I arrived to the end of my lecture. So I can summarize that there are several data sets for MOX-fueled sodium fast reactor available in open literature. They include specifications and real measurements, reactor measurements, and they can be used for validation of coupled neutronics, some thermohydraulic and mechanical calculational codes. Thank you for your attention.
Okay, thank you so much, Professor Konstantin, for your interesting lectures. So now let's move to the Q&A sections. I find there are students asking questions in the chat. So can you see that?
Yeah, I see it.
Okay. Yeah.
So maybe I will read it. Yeah.
Okay.
Professor Konstantin, thank you for your great lecture. Welcome. I have 2 little questions. First, for transient rod ejection accident, control rod will be removed from the core with high velocity during a short time. Different neutron space kinetics codes, like Parks and in3D, may have significant differences when predicting the power and reactivity change over time. For this type accident, which has a fast transient behavior characteristic, which method do you think is better to choose, direct simulation or improved quasi-static method, or empirical point kinetics with reactivity composition? Okay, my answer here for this specific transient, of course, you are very welcome to apply space kinetics and maybe even transient Monte Carlo. Yes, it would be very interesting to see the results, but the level of knowledge we have for this transient is not very high. Yes, as I said, we took first, we didn't know very exactly the specification of the Superphenix reactor. What we did is we search a lot of open data, yeah, a lot of papers, and we try to collect description of the core from different sources. You know, sometimes then give one number in one paper, another number in another paper, and we tried to spend some time to summarize and create a Superphenix model. We intentionally didn't ask CEA or EDF about their data because these data are sensitive. If they give them to you, then you cannot publish the results. So what we did, we created best what we can for the model, but it's not ideal. Yeah, we don't know exactly what is the level of uncertainties. Second point that, as I said, especially for this transient, extremely important is fuel rod behavior. And you can imagine that we have a huge number of fuel rods which are expanding in a different way, and to predict accurately the average fuel temperature, which we need to describe the evolution of power, we need very detailed knowledge about the fuel. And what we did, we used one representative fuel. Yeah, you feel that there is some high uncertainty. And in my opinion, the level of this uncertainty best fits the point kinetics with simple fuel rod model. And point kinetics can give us the good answer. That's what we see. And if you would like to apply special kinetics, then in a way you will check your special kinetics against point kinetics. It's a bit paradox, but because of this special situation, it's like this. So yeah, both improved quasi-static and direct simulation are good ideas, yes, because IQS can give you gain in time calculation, yeah, can save time. And second question, how do you currently think about the use of Monte Carlo method to calculate reactor space-time kinetics problems? People are doing great progress in European projects in particular. MaxSafe, if I'm not wrong. I was not part of these projects, and I think that it's still a far way to go, because yes, we can do sampling with these time groups, yeah, but delayed neutrons is still an issue, and feedbacks also not readily available. So I don't think that at the current stage we can use transient Monte Carlo for design calculations. Maybe we can use it for some kinetics benchmarks, but also I'm not so sure. We need to see the level of statistical uncertainty we have. Okay, I go to, yeah. Thank you for the first question. The second one, thank you for your presentation. Welcome. I have in page 58, why is there a great deviation between the computation values and the computation and the measured values during the 2000. I wonder if the model can be further optimized. 58. About 58. This one. Can you see it on the screen, the slide? Do you see the slide on the screen?
Yeah.
So, yes, okay, thank you. Well, I think, yes, this is again, I can only repeat what I just said, that there is a big uncertainty and big difficulties of predicting correct evolution of fuel temperature and therefore Doppler, because of very complicated thermal expansion of fuel and then reduction of gas gap in very many fuel rods. And then it sums up everything to Doppler, and this is a challenge. And then for the reduction, yes, for the last curve which goes down, we also need thermal mechanical effects. Yeah, these effects related to contractor rod driveline expansion. They are small, but you have to predict them accurately. So you can imagine that we spend a lot of time to get as good as possible picture. but always there is a place for improvement. So maybe if you simulate all fuel rods or a fuel rod for every assembly, then you can improve Doppler prediction. Thank you for the question.
Okay, thank you.
Okay, I
there-
don't see other questions. Maybe
Okay. Yeah, there is another
you can
question
ask
from-
by voice.
Yeah.
Sorry, Professor.
Yes.
Yes, I have a question. In our laboratory, we also have a system code for SFRs. It's called Cycles, and we developed for almost 10 years, and we're still developing it. So I just wondering where we can find these benchmark specifications so we can validate our code. Yeah,
Yeah.
we know some benchmark specifications such as the Phenix nature circulations. We validate all our code use this benchmark, but other benchmark specifications it seems we couldn't find it in the open literatures.
Yeah, it's everything, as I said, described. We tried to give every number which you need in this paper. So if it's not, it's open source journal. But if you cannot get access, I will send it to you later.
Okay, thank you.
Sure, welcome. Any
Okay,
other
thank you,
questions?
Professor. Yeah, there is two questions in the chat from Mr. Liu Yapeng.
Okay, yes. Thank you, Yapeng. You are welcome. For security analysis, the calculation needs to ensure conservative. So what will these programs generally do in terms of the conservative treatment? Well, yes, I know that when you, for example, when you simulate loss of coolant accident, yes, for licensing authorities, you should make with something like RELAP 5, you should make conservative assumptions. Yeah, like you can say my reactor started at 110% power because it can be there. Yeah, it can oscillate. Or you say that my power peaking factor is multiplied by engineering coefficient, just to be safe, just to go. And this is very typical in licensing calculations, because then you convince safety authority that you analyze the worst scenario. So here we are a bit different in different environment, and our goal is not to convince safety authority yet. Yeah, maybe we'll do it later, but now we would like to validate our codes. We would like to understand the physics, yes, all these expansions, how Dopplers work and how important gas gap conductance is. And in this sense, to impose additional how to say the limitations, yes, or some conservative coefficients doesn't make much sense. I think we are happy when we see that yes, we catch the physics, yeah, we reproduce the measurements, and now we understand something. So now our model is a little bit more able to predict physics. And this is not that we say this reactor is safe in this situation. So maybe, yeah, the goals are different slightly. But we should have it in mind, I agree. What are the disadvantages of sodium-cooled fast reactors? The operation time of Superphenix reactor is very short, and Europe has not continued to develop sodium-cooled fast reactors. So in my opinion, there are no disadvantages of sodium-cooled fast reactors. This is the best reactor. But to be serious, yeah, of course, we should be careful with safe with barriers. yeah, to practically eliminate some things like contact of primary sodium with water. Yeah, by introducing intermediate circuit, we practically eliminate the possibility of contact of tertiary water and primary radioactive sodium. Or we make special measures to engineering measures, yes, to improve the barrier. For example, in SFR Smart, we consider welding all connections for primary pumps, for example, for eye checks. We consider welding them. So we do all engineering measures to improve reliability of barriers, to avoid the contact between sodium and atmospheric air or water. One thing. Second thing, which is not unique to sodium-cooled fast reactor, is positive void effect. And here we are doing also a lot of things, starting from sodium plenum. Now in a new European project, SFR Simple, we are studying metallic fuel in ESFR, in European sodium fast reactor, and we are excited to see how metallic fuel will behave in unprotected loss of flow. Maybe we will show that we can avoid sodium boiling even because of the properties of this fuel. Yes, and also, yeah, reliable SCRAM system. Reliable SCRAM system, it's very reliable piece of device, yes, and the probability that it fails is very small. So still, we have all solutions of these few problems, but the advantages is multiple, yeah. And the main advantage maybe is absence of corrosion. So due to proper chemistry control of sodium, we practically eliminate corrosion. Okay, it's like in gas fast reactor almost. You're welcome.
Okay. Okay, thank you, Professor. You have given us detailed introduce of the 5 benchmarks from the Phenix and the Superphenix, and also thank you so much for your will share the detailed parameters of these benchmarks with our students.
Thank you very much.
You are so kind, yeah, and also you have answered so many questions. So since we have another labor meeting in 5:30, so I'm sorry to end the lecture half an hour before our plan. So thank you so.
Thank you for inviting me, and keep your great work. Thank you. Goodbye,
okay. Thank you,
everyone.
Okay.
Goodbye.
Okay. Goodbye.